Okay, it is time to talk about microphones. Now, how do they work? Well, in a lot of cases, it's magnets or at least electromagnetic induction. Let's start with the basics. For an analog to digital signal path, you have analog. This is a continuous signal that must be converted into a digital collection of samples before we can use it on the computer. The signal is picked up by a transducer, which goes to a preamp, which goes to an analog to digital converter, which goes to the computer as digital data. In this case, the transducer is a microphone. The preamp is boosting the signal and takes that really small electrical signal from a mic, especially from a dynamic or a ribbon mic, and boosts it for the ADC so that it can convert and you're not going to have a bunch of really quiet values unless you want that. Going the other way of digital to analog, you have digital data going to a digital to analog converter, to an amp, to speakers, which become sound waves that you hear in your ears. So how do mics work? Basically, they are converting acoustic vibrations from air pressure changes into electrical energy. Typically, you have a diaphragm in the mic that is vibrated by air, connected to a magnet set within another magnetic field. When two magnets within the same magnetic field interact, you get electricity. It's a very small amount of electricity, but that's the result. That is then sent out, amplified, and converted. There are three primary types of microphones that we're going to be looking at: dynamic, ribbon, and condenser. All of those are going to use some form of diaphragm, transducer, and a case, all of which are going to have an effect on the overall sound of the mic. So here is a microphone, and here are the parts. Up at the very top, you have the grill, that mesh area that's covering the capsule. And the capsule has the diaphragm in there. That is the part that is going to be vibrated and will convert those vibrations into an electrical signal. Below that, you have the case, which covers the transducer and all of the electronics. And at the very bottom, you have the output that goes to your interface. The diaphragm is a thin membrane of metal or plastic. Sound waves hit it, it vibrates. It is incredibly thin. They measure these in nanometers or micrometers. So as a result, it can reproduce really high frequency sounds because it doesn't take a lot of air pressure to get it to vibrate. Unlike, say, if you did it in millimeters or inches. The transducer converts those mechanical vibrations into electrical signals. Again, it's usually using one magnet suspended in a magnetic field of the opposite polarity, and that produces electromagnetic induction, which creates an electrical signal. The case is probably the most important part. It protects the diaphragm and the transducer, and it can also control the directional response of the mic. Some mics are going to be built so that the diaphragm is right at the end of the case facing straight out. Some are going to be side addressed where you have a grill covering them, and others might have different cases that are used to get the mic to bend and get into hard to reach areas, like if you're miking a drum kit. So again, there are more than one type of mic. Let's start with the dynamic. This is the classic Shure SM58 handheld vocal mic. You know it, you love it. Dynamic mics are the most commonly used mic due to the ability to get close to a sound source and take significant abuse. They work by electromagnetic induction. Again, the diaphragm is attached to a magnet in a magnetic field of the opposite polarity. They vibrate, they create electricity. This has a couple of really good advantages. No inherent electrical current, which means if you happen to drop it in water, you're not going to ruin the mic, maybe, hopefully. Don't try it, but it can probably survive a little bit of moisture. Also, it is going to be really dependent on the weight of the mic as to what frequencies it can reproduce. Generally speaking, but not always the case, a lighter dynamic mic is going to be able to reproduce higher frequency ranges if that diaphragm and transducer in particular are very light and easy to vibrate. Drawbacks is that they frequently have a really quick roll-off above 10 kilohertz on the frequency response. They typically also have a little bit of a resonant frequency boost, usually around that 1 to 4K mark, but that makes it pretty good for adding presence to vocalists. The main advantage is they are excellent for really loud, high-pressure sounds. They can get super close. You'll notice that my mic right here is nearly touching my mouth. The pickup range is smaller than condensers as well. You get maybe 6 inches to a foot depending on the mic. That's really good if you want to control bleed from other signals. So you don't want your vocalist who's singing into the mic to also pick up the guitar. They are extremely robust and super resistant to humidity. And I'm really serious about this. I've seen mics fall into pitchers of beer at gigs. I have seen mics get rained on. Dynamics are fine. Condensers will die. Also, as an advantage, they are generally low to moderate cost. Usually, a good dynamic mic will run you about $100 to $200. Some can get much more expensive, though. There are some really good ones that are up in the $800 to $1,000 range, and they do go higher. So here is the main part of the dynamic mic transducer. You have the diaphragm, the voice coil, and the magnet. The voice coil is just another magnet that is moving in a different polarity from the static magnet. Next up, we have the ribbon mic. And here's a really nice photo of a ribbon mic. You can see the various parts, the case, the kind of weird rectangular object is the ribbon mount and ribbon itself. And then over on the left, the 2.5 taped unit is the transformer that is used for the mic. So ribbons work on the same principle as the dynamic. You have a really, really thin piece of metal, usually aluminum, can be other things, suspended between two magnets. And vibrations hit that metal, and it generates an electrical signal. But it is a really, really small electrical signal, so a transformer is required to boost the signal, period. Because of the ribbon, the upper frequency response rolls off a little bit higher at 14K as opposed to 10K for the dynamic. Very, very neutral responses with ribbons. They tend to take EQ really, really well and be very, very flat response-wise. But there is a drawback. By definition, ribbons will pick up on either side of the ribbon. So you have the front of the mic, you have the back of the mic, and it can get sound from either direction. This can be very cool, or it can be a huge annoyance. Also, they are generally able to handle much higher sound pressure levels than any other mic, which is why ribbons are classically used on guitar amps, among other things. The drawback is that they are super, super fragile. If you touch the ribbon, it will break, period. With some of the classic ribbon mics, if you store them in any way that is not vertical so that the ribbon is standing up, they will break. You can also blow out a passive ribbon mic by accidentally applying phantom power. That is not good because getting a ribbon replaced will cost you anywhere from several hundred to several $1,000s. And ribbon mics are expensive. You're looking at around $1,000 for starting, and they only go up from there. But on the upside, they are super neutral. They take EQ better than any other type of mic out there. They have a great natural sounding high-end response, and they can handle extremely high sound pressure levels. So amps, if you're recording a full orchestra, if you're recording a pipe organ, ribbons are all very strong candidates for those particular applications. And once again, here's a picture of the ribbon transducer itself. It's that corrugated strip of aluminum suspended between two rare earth magnets. Boy, these things look cool. Next up is the condenser, the classic. They typically come in two types. On the left, you can see what is called a large diaphragm condenser. And on the right, and definitely not to scale, you have a small diaphragm condenser. Condenser mics use two electrically charged plates, one as a diaphragm and one as a fixed backplate, that form a capacitor or a condenser. Sound waves move the diaphragm closer to the backplate, creating a change in capacitance, which results in a voltage change. Because of this, they require power. They have to have either phantom power, the plus 48 volts, or a battery to power a mic, or they can have tubes and transistors, either built into the mic or as a separate unit. It's very common for vacuum tube mics to have a separate unit that you have to plug into the wall with a special 6 or more pin connector that goes to the mic, and then a standard XLR that you can plug into your interface. By default, condenser diaphragms are actually in an omni-response pattern, but you can change the directionality by applying holes that are punched in to delay the arrival of sound at the backplate, so it happens at the same time as the diaphragm and is thus canceled out, creating different polar patterns. You also have multi-pattern condensers that use a single backplate suspended between multiple diaphragms and vary the amount of signal that's applied to each diaphragm that goes to the amp. And this will give you the ability to go from an omni to a cardioid to a figure 8, and on the vacuum tube based ones, you can usually morph between those, which is a really cool thing. All condensers, by and large, have a slight resonance point between 8 and 12 kilohertz, although the exact point will vary depending on the manufacturer. So, phantom power and how you power your condensers. 48 volts DC, fed from a console, preamp, or interface. This is the plus 48V button. It's usually switchable on groups of channels on prosumer and consumer level gear, and on really high-end gear, it is switchable on each channel. That is a really, really cool thing, and if you can afford an interface that does that, and you're going to be doing a lot of recording, I recommend getting that. Downside of this is that it does cause pops when disconnecting a mic if you leave the phantom on, and be aware that while phantom power will have no effect whatsoever on a dynamic mic, on a passive ribbon mic, it can destroy it. So make sure you know what type of mic you're plugging in. Do not blow out that vintage ribbon mic because you forgot to turn off phantom power. Another way of powering condenser mics is batteries. Typically, these will be either 9-volt or multiple AA's or AAA's, but now we are seeing some condenser mics shipping out that have built-in batteries that can be recharged over USB. Then the other traditional way is having a powered amplifier. Specialty condensers, or those that have a tube preamp, will have to be plugged into the wall. They come with a little box that has the vacuum tube, that has all of the electrical stuff inside of it, and then it will take power from the wall, convert that to something that the mic can use, and send it to the mic. And on the really cool ones, you can also morph the pattern that it's using right there on the tube amp. So here's a diagram showing a end address condenser. You have the diaphragm and the backplate. Both are powered. When the sound waves hit, they vibrate the diaphragm, bringing it closer to the backplate, which creates a change in voltage that is sent out. Large or small diaphragm condenser, that is the question. They both have great properties, and they both have some drawbacks. So it really is going to depend on the application. I personally recommend that you have at least one of each. For the large diaphragm condenser, they will typically be side address. You're not going to speak directly into the end of the microphone, but into the side of the grill. They have better pickup of acoustic energy because they have a physically larger capsule, but they have higher output voltages, so your signal to noise ratio is also going to be smaller. They are excellent things for close miking, quiet sources. They are also great for rooms and ensembles if you have a pair of them. They also have a little bit better bass response, if only because of the size of the diaphragm. That tends to be really nice. But they also tend to color and shape the sound more than a small diaphragm condenser. The grill around the capsule itself can create internal reverb and filtering effects that you can notice. On some, it's very transparent and you're not going to hear it. On others, it will be apparent. They also tend to sound a little bit warmer, I guess would be the best word, to have a little bit more presence in the mids and the highs than, say, a small diaphragm condenser, especially some of the classics like the Neumann U87 or the Mojave MA301. Small diaphragm condensers, by contrast, are typically front address. They also typically can have a little bit more self-noise than some of the large diaphragm condensers. Not always the case, though. Some of the really high-end Sennheiser MD series actually have less self-noise than pretty much any other mic on the market. But small diaphragms, generally speaking, have significantly better transient response. They also have a better high-frequency response and are very consistent in terms of the pickup pattern across the entire frequency range. And unlike large diaphragm condensers, they lack off-axis coloration of the sound. Also very useful is that the frequency response tends to be a little bit more neutral and less colored. So what you're hearing is going to be closer to what you would be getting. And more importantly, they are smaller physically. They can be called pencil mics for a reason. They can be placed much easier in tight situations. So which to use? If you're recording anything really quiet, solo instruments, voice, or low frequency sounds, drum overheads, rooms, anything where ambience or reverb is necessary, or if you want to get that single sound by having a group record around a mic and get that vintage feel, or any situation where you want rich and warm and larger than life, that is a large diaphragm condenser. For small diaphragm condensers, they work really well on acoustic instruments, especially strings and especially plucked strings like guitar, mandolin, stuff like that. They work really well as room and ensemble mics if they're in a stereo pair. They also work really well on percussion because of the transient response, especially on snares and cymbals, in orchestras as a stereo pair and as spot mics over sections, and any situation where you need pure and natural sound with a really good amount of stereo separation between the left and the right. So the drawbacks to condenser mics, they're expensive. You can find condenser mics on the cheap side from companies like CAD or MXL, and they'll be okay for a home studio, but condenser mics get very pricey very quickly, with some running into the thousands of dollars to the tens of thousands of dollars for some of the classic tube mics. Low-cost models in particular are very inconsistent. They do not have the quality control at some of the factories that are turning them out, one after the other, doing 1,000 models per minute. They do require power, and they can be very, very large. Just as an example, a Mojave 301 weighs 1 pound on its own, and even more when you add the shock mount. Compared to that, an SM58 weighs about a half a pound. Also, unless they are a factory-matched pair, two mics of the same model will sound slightly different. And then more to the point, condensers are sensitive to humidity and temperature. Using them outside is generally not a good idea. Also, more importantly than even that, they have a larger pickup area. They can definitely intensify bleed or loud instruments. I've recorded sessions where I've had harmonium or accordion in, and the band wanted to track that live, and that was so present on every track that I didn't even have to put a mic on it. It bled through every other mic in the room. But there are advantages to condensers. They have the best high frequency response of any type of mic. They have great low frequency response as well, but it's subject to the proximity effect, which we'll talk about later. They have excellent transient responses. They are very crisp and they sound like it. And on the large diaphragm condensers, switchable polar patterns make them incredibly versatile for different applications. There are some myths about condensers, and I just want to clarify a couple of these. So all of these are false. Large diaphragm mics always have better low frequency response than any small diaphragm mic. This is false. There is a huge amount of variance between different manufacturers and even different microphones from the same manufacturer. Also, keep in mind that Omni mics are probably going to be your best bet for low frequency response. So if you're comparing polar patterns, make sure that that is something you think about. Cardioid mics have better responses than Omnis for condensers. Not necessarily. It depends on the mic, not on the polar pattern. Large diaphragm mics have a flatter response than small diaphragm mics. This is not true. They are slightly warmer and have a slightly higher mid and high section. Small diaphragm mics are quieter. Not necessarily. It depends on the mic. And condensers are consistent from mic to mic in non-matched pairs. Absolutely not. They can be very close, but unless they are factory matched, they are probably going to have some significant differences that you will hear usually. Okay, so next up, this is the Electret, which is a sub-style of the condenser. Electret mics use a permanently polarized diaphragm, avoiding the need to use any type of biased voltage like battery or phantom power, like a regular condenser would. Now, this lets manufacturers make them really small and really expensive. Like, you can get them on Amazon for $1 per mic, but you'll have to, solder them onto your own cables. They are found on cell phones, portable recorders, in just a lot of different applications for consumer-grade electronics, but generally, some are good, but most of them are terrible because they tend to lose their charge over time, effectively dying. I'm not saying that there are some bad ones. There are some very good ones out there, but in general, the consumer-grade ones are pretty awful. However, because of their very, very low prices, they are really cool if you want to do your own projects and installation art. Like if you wanted to build your own binaural mic by getting a dummy head and sticking some mics into molded ears, you could do that pretty easily with some Electret condensers. In fact, there's videos on YouTube. So they're very simple. They have two terminals. One is a ground and one is the output. That's it. Other mics to be aware of are USB mics and wireless mics. USB mics connect directly to the computer via a USB cable. There are generally going to be low-quality condenser mics like the Blue Snowball, which is okay for video conferencing, but I would never record with. There are better ones like the Neat Beecaster or the Blue Yeti, but even then, I would still prefer a dedicated mic and an interface. Also, for Windows users out there, be aware that due to how Windows handles audio devices, you typically can only use one USB mic at a time. If anything, the pandemic has really driven this home, as I've had to answer that question many, many, many times in the last several months. Next up is wireless mics. Wireless mics are going to operate by sending a signal via a radio antenna in the mic to a base station at the console. Typically, you have wireless mics that are lapel mounted, which are usually connecting to a belt pack, stand mounted, where they usually have the transmitter built into the mic, or handheld. Again, the mic will be having the transmitter built into it as well. They are almost exclusively dynamic, but there are a few very expensive condensers that exist. The quality varies significantly. Some are okay, some are better, And some manufacturers even make better capsules to replace the stock ones on inferior mics. For example, SE Electronics has a wireless capsule of their V7 mic as a replacement for Shure's SM58 capsule. It's a huge difference, and it's a very attractive one. So let's talk about the microphone specs. How do you read these charts that come with them or that you see on Sweetwater or Musician's Friend or Vintage King or Reverb? Well, let's talk about sensitivity. How much output is produced by a given level of sound pressure? This is roughly an indication of how loud the mic is. Generally, ribbon is the quietest, followed by dynamic, followed by condenser as the loudest. But the signal chain will make a huge difference. If you overload a condenser, you're just going to get distortion. Nobody wants that. Also, with ribbons, if you turn them up too high on some models, you will get electrical noise. Be careful. Sensitivity is generally going to be rated in decibels, and different makers use different ratings. But in general, the closer to a sound you are, the louder the output will be. This does not mean a mic is better. It just means that you have a louder output at a closer distance. Overloading is when you press beyond the mic's ability to handle a sound source and it causes distortion. Typically, there are a couple of ways to do this, but it's usually prolonged exposure to a really loud sound and not just a transient like a snare hit or a hand clap. Permanently overloading for a prolonged period of time can permanently warp a mic's response. This is why in a lot of studios you have a dedicated mic for the kick and snare drums that are labeled as such and not used on anything else. So frequency response is equally, if not more important than the mic sensitivity. You can always get a preamp to boost the sensitivity, but the frequency response is going to be the most important thing. How does a mic respond to different frequencies? Does it boost some things? Does it cut some things? How flat is it across the spectrum? As flat as you can get is going to be ideal for taking an external EQ, but it's not always ideal for every job. For singers, you might want a mic that boosts some of the upper partials to really make their voice sparkle. For other applications, you might want a mic that cuts out lower frequencies in order to get rid of bass or to not have to deal with any possible bleed from a low frequency source. You may want to use a mic with a high-end boost to level out bass. Now, problems with frequency when you're listening are typically due to off-axis recording. Is the mic capsule pointing directly at the sound source? This is something you will notice in particular with singers, that if they're not paying attention, they tend to move their head and dance around a little bit, kind of like that, and their mouth gets away from the mic, and you start noticing weird sounds, and the frequency will shift and change a little bit. That is off-axis recording. You do not want that. Manufacturers will typically provide charts showing the response to their mic, including different polar patterns and how they respond across the different frequency spectra. So here's an example of a mic. This is a multi-pattern mic. It has OMNIDIRECTIONAL and figure 8 patterns. You can see that they all kind of come to a flat response at around 1000 hertz, and then they space out on either side of that, giving a little bit of a boost to everything below and everything above, but just kind of coming in and notching down a little bit on that 1K response. Self-noise is another big issue. This is mostly going to be an issue with condensers. They are the most prone, but this is noise that is either self-generated in the mic or caused by handling it. This is why we have shock mounts. Condensers are the most prone to self-noise. Specifically, any electrical noise the mic produces will be amped before output, making any hum really noticeable. And you can only do so much to filter this out. Dynamics and ribbons don't really have a lot of self-generated noise because, again, they don't have a lot of electrical current going through them, just whatever they're generating, but they are really sensitive to being bumped or touched. So again, use your shock mounts. Self-noise is commonly measured in dB-A, which is weighted for human hearing because we don't hear the low frequencies as well as the higher ones. Most reputable manufacturers will also give stricter measurements using soundproof chambers, but not all of them will make that easy to find because you might see super awesome mic specs and then some crazy manufacturer-specific self-noise measurement that you've never seen before. Levels of self-noise, this is what you should be looking for if they publish the specs. Anything less than 10 dBA is excellent, but will probably take a big chunk out of your wallet. In most cases, the room itself is going to be noisier than the mic. These are almost exclusively going to be large diaphragm condensers, although Blue's Hummingbird is a small diaphragm condenser that's whopping 8.5 dBA. 11 to 15 is still excellent. There's going to be some noise, but it's nearly going to be impossible to hear in a mix. Most large diaphragm condensers, tube mics, and the higher end small diaphragm condensers will be in this range. 16 to 19 dBA is the good enough range. There's going to be some noise, but it will be manageable for almost every mix, but it's not good for really quiet sources. You're going to notice when you bump the source up that you hear a little bit of hissing noises on the track. You want to avoid those. 20 to 23 dBA is really, really high self-noise. You definitely don't want to use those unless you're recording something really, really loud. And anything above 24 dBA is unacceptably high. Do not use ever. These are the things that, you get for free with your karaoke machine. Don't use those to record. Now, how a mic responds to sounds coming from different directions around the mic will be heavily dependent on the casing of the mic, not necessarily the type of mic, whether it's an LDC or an SDC. That will also come to bear in the self-noise. A lot of that is also going to be displayed on a polar diagram, which looks like a bullseye. The polar diagrams, which we're going to be talking about pretty extensively, show the level of pickup from all angles at different frequencies. The polar response determines the mic's usefulness in different situations with the 0 degree position at 12 o'clock if you're thinking of it as a clock face. End address mics, the 0 degree position is going straight into the grill of the mic. This is most common on small diaphragm condenser mics, dynamic mics, etc. Side address, the 0 degree position is into the side of the grill, typically the one that has the manufacturer's logo on it. This is common on large diaphragm condenser mics and on ribbon mics. So here's an example of the polar patterns. We've got 0 degrees and then going clockwise 30, 60, 90, 120 all the way around to 330 and then back to 0 or 360 degrees. Just always assume the mic is at the center of this clock face and it is pointing up at 0 degrees. So you can see this is a multi-pattern mic and it has different responses, which we'll talk about right now. Omnidirectional. This is picking up sound from all directions. It's a 360 degree sphere around the mic itself. It is not subject to the proximity effect, which is very good because it means you can get very close to a source without any unintended bass boost. It is a very, very good response for percussion, especially when it's used in a stereo pair. I've found it works amazingly well as overheads on marimba, and it's very good for close miking any source you would want to use. So here's the Omni pattern. It's just a big old sphere. Next up is the figure 8. Any guesses as to what that particular pattern will look like? The figure 8 picks up signals from the front and back more or less equally. There's usually just a slight cut on the back, but it doesn't pick up anything on the sides. The frequency response tends to be slightly brighter to the front, but that's about the only major distinction between the two sides. They are great to use when you need to minimize bleed from the side, and it is a classic pattern used to mic up a guitar amp. They can also be made more directional by adding sound-absorbing material behind the mic. It's very common to use foam behind each mic on a pair of Royer 121s. I've seen that many, many times in studio and have done the same thing myself on more than one occasion. And here is the figure 8 response. Up next is the cardioid, which is heart-shaped, hence cardioid. Although keep in mind that in three-dimensional space, this will really be more like a kind of an apple-shaped. It gives a very increased front directional response by punching holes in the diaphragm of the condenser. There is some side bleed, but there is really good rejection on the back with a null point exactly behind the mic. This is probably the most common shape of mic you will find because it's so directional. It's really great for picking up sources. And here it is. If you were to tilt this 180 degrees, you'd kind of have a heart. But again, remember, in 3D space, this is going to be more apple-y than heart-y. Related to the cardioid is hypercardioid, which you'll also see called supercardioid. This has a thinner front response than cardioid, but it's even more directional to the front and has better side rejection. But because of that, it has a slight pickup behind the mic. There is no null point directly behind the mic like you would have on a true cardioid. However, that makes it excellent for a vocal mic, in particular dynamic vocals. Here is what the hypercardioid looks like. You've got the very directional cardioid up front. It's a little bit thinner than the standard cardioid. And then in the back, you have a smaller pickup area. It's not big enough to qualify as a figure 8, but it will still pick up things behind the mic. Now here's the proximity effect. So the proximity effect is a bass boost by having your mic too close to a sound source. You can see that the globes are showing how sensitive it is, that you're getting that 125 hertz and also 1 kilohertz boost depending on the proximity of the mic, that as you get closer, it's going to get even more pronounced. This is something you want to avoid at all costs in order to not have any unintentional boominess in your mix. Cardioids and hypercardioids are subject to the proximity effect. This is really going to be prominent, especially on condenser mics. Omni mics, however, are not affected by it. Now, if used carefully, it can add some warmth to sounds and make a thin, high-sounding instrument sound a little bit more natural and bring the frequency down a little bit. But if you are not careful, it will make everything sound extremely muddy. So you have to be aware of that and know when to avoid it and when it can be useful, but mostly when to avoid it.